The information age has created an unprecedented production and consumption of data. With this surge, data analytics have become increasingly important for making predictive models in transportation, online shopping, meteorology, social media, cryptocurrency, and many, many more. Machine learning with deep neural networks has been at the forefront of these predictive models, and now we're expanding their scope to include different forms of data. Historically, time series forecasting has been used for prediction, i.e., we use the past to predict the future. But what if we looked at more than that? What if we looked at multiple pasts of many different things simultaneously and let those signals interact with each other to form better predictions? This is what state-of-the-art graphical neural networks can achieve, and in my project, I'll be applying it to the stock market to see just what it's capable of doing.
Howdy, my name is Maxwell Huffman, and today I'll be covering my research and senior design project, Interconnected Financial Prediction using Time Series and Network Data. My faculty sponsor is Dr. Yang Shen, who I would like to thank for his patience, wisdom, and optimism while researching. The ultimate goal of my research was to create a predictive neural network that utilizes both sequential and relational data, so anything that has dependencies on time and a relationship with other entities in a network would fall into that category. For this thesis, my hypothesis was that the inclusion of relational network data would improve accuracy in financial market prediction. I validated and measured my results against three metrics: the amount of money earned, which is the intraday return ratio, how well the model predicts the next day price, which is the mean squared error, and comparison against average. As of February 2021, the market capitalization of the top 19 stock exchanges in the world is $97 trillion. So improving prediction accuracy in this field has value because more accuracy means more financial success, and there's clearly a large market for it. So given that we have a backlog of stock market history data and we have money to invest, our model needs to answer the question, which stocks will increase in value the most by tomorrow? To define what most means, let P be the stock price and T be today. Our model knows the stock price of today, and it will try to predict the stock price of tomorrow. Calculating the return ratio for tomorrow normalizes those results so that all we have to do is choose the stock with the largest R value that we think will grow each day. To get those predicted prices, we start with a long short-term memory cell, otherwise known as an LSTM cell, which is a standard recurrent neural network used in machine learning. If we abstract away all the linear algebra, basically the cell takes in a value for time t, which is our history, and gives an output for time t plus 1, which are the embedded predictions. However, the cell also uses information from the previous time step informing that prediction, and it passes its data to the next time step. If we bundle all these cells together, you have an LSTM neural network model capable of learning temporal patterns. The training data we feed in are the closing prices and moving averages of 881 companies in the NASDAQ stock exchange, ranging between 2013 and 2017, which I have split into three groups, one for training, one for validation, and one for testing. The standard loss function, which teaches the model how to make a prediction, would normally be the mean squared error between the predicted return ratio and the actual return ratio. But to improve that, I implemented a rank factor into the function, which teaches the model how to rank stocks relative to each other, rather than just trying to predict their immediate next day price. But the model isn't using company A's value to predict company B's value. Rather, if the model ranks A as better than B, and it's wrong, then the model is heavily punished while training. Rank matters so much to our problem because if the model can rank the stocks in order from best to worst, then we're done. We've succeeded. To tune the rank factor, I trained 7 different models, each with a different hyperparameter alpha value, which I varied from 0 to 20,000, and graphed their returns in the validation set. As can be seen here, an alpha value of 10 produced the highest return. Not only did the alpha 10 model earn the most money, it also had the second lowest mean squared error, which are both better than the default LSTM. Then I ran the standard mean squared error LSTM and my alpha 10 model on the never before seen test set, and my tuned model was 30% better than average. Each day the models purchase the stock they rank as the best after looking at 466 days of history, sell it the next day, and then repeat the process. To calculate the black line average, we equally divide our capital among all stocks, which is the trading strategy involving the least risk. If a model can't beat the black line, it's useless. However, this was just step 1. Our alpha 10 model doesn't have any relational data yet. The stocks might be ranked each day, but their predictions are still independent from each other. To ease you into the graph theory, here's what an aggregation looks like on a sample relationship network where the company prices are the nodes and the edges are the learnable parameters. After one aggregation of one node, you can see that the value of Apple will become a weighted sum of its neighbors' values. This happens to every node. So if you train the value of those edges while making predictions, the model is capable of interdependent learning. However, to apply this to our time series model, we can't just use the stock price. If we go back to the LSTM model, we see that its output is vector E of t. This is the embedding which has captured the temporal prediction power of our LSTM model. At every time step t, we generate a matrix capital E, which contains all the little e vectors for every company. And if we concatenate each e matrix produced at each time step, we have a tensor comprised of TEs. These matrices are what our graphical neural network aggregate over. Our input relationship data is stored as an adjacency matrix, and we call it A. And the edges are connected if two companies share an industry sector, like manufacturing, computer, or retail. And if we aggregate the output embeddings of our Alpha 10 LSTM model using these industry relationships, we've created a hybrid model that can learn both temporal and relational information. To determine the relationship strength of those connections, we train a learnable function G, which we model in two different forms, implicit and explicit. In the implicit model, the parameters are learned by taking in company embeddings and their relationships. In theory, this approach gives the model the most information possible to learn what the strengths should be. However, I also implemented an explicit model where the parameters are only learning information from the adjacency matrix, while the two company embeddings are simply given the dot product, which is an explicit method of calculating similarity between two time signals. This gives us two different ways to try and learn relational information. The implicit model performed better than average, but worse than my tuned LSTM. And the explicit model did terribly, losing about 20% of its portfolio value over the course of the year. However, we're putting all of our eggs in one basket by only picking one stock. What if we chose multiple? Let's call this hyperparameter K, and let K be the number of companies that a model will equally invest in each day. So for K equals 1, we'd invest $10,000 in one company. For K equals 2, we split it 2 ways. For K equals 3, we split it 3 ways, and you can keep going. Let's apply that to our models. On the implicit model, the best value is K equals 8, but this looks like an outlier based on that huge spike. But varying K didn't seem to help much on the implicit model, aside from reducing volatility. However, the explicit model saw significant improvements for K equals 44 and above, even better than the implicit model for the same K values. This implies that the implicit model is better at ranking the best stocks, whereas the explicit model might be better at ranking stocks as a whole. Given the results for the NASDAQ set and these models, it appears like investors can choose to diversify their portfolios or have faith in the best stock that prediction is just the best choice. Both strategies were in the green, but they got there in very different ways. The last part of my project is what ties everything together, and that's my interactive Jupyter notebook that future data scientists and researchers can use to explore their own data sets. You can view features through time in the training set along with their neighboring features. You can generate any model I've described so far to your exact specifications, so type, loss function, activation function, hidden units, anything you want. And behind the scenes, datasets, models, and prediction outputs are handled for you in CSV and JSON files for ease of access. But more importantly than that, the visualizations and the assessments for each model are also included. So you can also calculate feature importance on the temporal models using perturbation, which shows you how strongly each of your predictors affects the final output. You can highlight days when different models made the same decision. Shown above is my tuned LSTM and the implicit model. So we can see that both models converge on the same choices near day 100, which is useful for just trying to understand what's happening. And finally, you can actually visualize the relationship strength between any company before, during, and after training to get a glimpse into what exactly the graphical neural network is trying to learn. On this dataset, the inclusion of relational data did not significantly improve my prediction results. However, we still greatly beat the average, and we're just scratching the surface of the power of relational models. What if we used better initial relationships? What if we modeled the strength function in a more sophisticated manner? What if we used a supercomputer in an enormous dataset instead? As of now, I have a solid framework with a stable machine learning environment, easy data curation methods, and interesting evaluation functions that myself or future researchers can use on any dataset they'd like. Like I already said, the world of machine learning with graphical data is just beginning, and I hope that my project can help others get started and expand the field themselves. Thanks, and gig 'em.